In the previous video, we did an introduction into how we think about solving these trig equations. And I listed a bunch of trig equations we're going to solve, and now we're going to solve them. However, what I'm going to do, let me just talk about the end of the last video. What I'm going to do is when I solve each of these equations, I'm going to give two different answers. The first one is going to be, I'm going to call it the general solutions. And if you recall the last video, that's where I'm going to, add the 2 pi n on to the solutions to account for all the times, all the different solutions as you continue to go around and around the unit circle. But then also, after that, for each problem, I'm going to go ahead and give the solution or give the angles between 0 and 2 pi. So for each problem, I'm going to give both of these different kinds of solutions. One, the general, which means you somehow show all possible angles that are solutions. And then second, I'll actually just do the solutions between 0 and 2 pi. So let's start doing some of these, and as we talk through them, hopefully you'll get the hang of it. If it's a little unclear right now, as you go through these, hopefully it'll click. Here's a equation I'm wanting to solve. Cosine of theta equals -1. So let's just talk through what we're actually looking for. We're trying to solve for theta. Theta is like my variable I'm trying to solve. What I'm saying is, let's go find all the angles that when you take the cosine of the angle, it equals -1. Right? So if you think about it, once again, this is why I stress learning the unit circle. If you go to the unit circle, let's go find an angle that the cosine is -1. And where is that going to be? Where the cosine is -1 over here, what angle is that? That's pi. So we say to ourselves, well, pi is going to be a solution. The cosine of pi equals -1. But then we realize, you know what? First of all, are there any more points on the unit circle where the cosine is -1? There actually is not. Over here at 0, cosine of 0 is 1, but we're looking for -1. So, one trip around the unit circle, there's actually only one angle that is a solution. But then we have to take into account that, we can make multiple trips around the unit circle. So what we do is, we have to add on 2 pi times n. And let me just do this once more so it's clear what we're doing here. If I were to make a chart where I set a value of n and then I figure out what my theta is, for this solution, you always start with n equals 0. So if n equals 0, my theta is pi. And that's what I get as my solution on my first trip around the unit circle, trying to find a solution. Now if I said n equal to 1, I have 2 pi plus pi. My angle is 3 pi. So what is 3 pi? 3 pi is one trip around the unit circle And then you stop here again at pi, and of course the cosine of that, once again, would be -1. And then, if I decide now to bump n up to 2, you plug in 2 for n, theta would be 5 pi. And the cosine of 5 pi would be -1. So these are all solutions to this equation. But of course, we don't want to have to, every time we have a solution, write all these out. If you plug in 3, I would have 7 pi. So a very economical and sort of clever way of expressing all these solutions are to write it like this. Because you see, in this case, each of these solutions, it increases by 2 pi every time. So we write it like this. So the solution to this equation is theta would equal pi plus 2 pi times n. So this is what I call the general solution. Now, if I want the solution just from 0 to 2 pi, now here's what you have to do, and in future problems this is going to become important. You don't just assume the first 1 or 2 solutions are it. You actually have to go in and start plugging in your values of n, and you start increasing the n's until your angle is greater than 2 pi. So I go over here, I start with n equals 0. When n equals 0, what's my angle? My angle's pi. Since pi is less than 2 pi, then I know one of my solutions is going to be pi. Now I bump up n to 1. When I said n equal to 1, what's my theta going to be? It's 3 pi. But now 3 pi is bigger than what they want me to look at. So then I just stop. And I realize, okay, between 0 and 2 pi, there's only one solution. Theta will equal pi. So this is a general solution. When I want to find a solution within a certain range, I have to just start with n equals 0 and keep increasing my n's until my angle gets larger than the 2 pi here. Let's do another one. This is going to look a little, actually I didn't write this on the other video, but I still want to do it. At first it might look a little more complicated. I'm doing this problem because I want to stress to you the two-step process to solve this kind of equation. The two steps are, the first step is you have to isolate or get the trig function by itself on one side. And then the second step is, once you have the trig function by itself, you look and actually determine the angle that's a solution. So first of all, in this problem, we're trying to determine theta. First step is I need to get the trig function, which is cosine of theta, by itself. So I'm going to add 5 to both sides. So I end up with 2 cosine of theta on the left-hand side and 1 on the right-hand side. The trig function is not yet by itself. I've got this 2 here. So I'm going to move or get rid of that. So I'll divide both sides by 2. So now, it's like step 1 is complete. I have the trig function by itself on one side. Now the second step is to look at this and to start determining the angles for theta that would be a solution. So here we go. Let's go and see. I'm looking for an angle where the cosine equals 1/2. So I'm thinking of my unit circle, and I'm thinking, first of all, I realize the cosine's positive. So I'm going to be in quadrants 1 and 4. Right away I realize I'm in either quadrant 1 or 4. And then I say, so what are the angles where the cosine is 1/2? And I realize in quadrant 1, the cosine is 1/2 at pi over 3. And then I say, how about in quadrant 4? Is there an angle in quadrant 4 where the cosine is 1/2? Yes, it's 5 pi over 3. So one trip around the unit circle, I've got two possible angles as solutions. So now what I have to realize is, of course, when I start making multiple trips around the unit circle, I can have a lot more solutions. So I take that first angle, the angle in quadrant 1, and I go ahead and add 2 pi into it. And then the second solution will be written as, I take the 5 pi over 3 angle, and I also add 2 pi into that. So this is what I like to call my general solution. This is all angles, it's a solution. So now let's say that we want to determine the solutions between 0 and 2 pi, in a sense, one trip around the unit circle. Now I'm going to just do this, even though a lot of you know the answer, but just as a habit, I'm going to say, okay, start with n. When n is 0, my first equation gives me pi over 3. My second equation gives me 5 pi over 3. How about when n equals 1? My first equation now would be pi over 3 plus 2 pi. 2 pi is like 6 pi over 3. It would give me 7 pi over 3. The second equation would be 5 pi over 3 plus 2 pi. It's 5 pi over 3 plus 6 pi over 3. That's like 11 pi over 3. And now I look and I realize 7 pi over 3 is larger than 2 pi, so I don't include that. And 11 pi over 3 is also larger than 2 pi. So basically, I don't have to keep going. Matter of fact, the only angles that worked are when n is 0. So for this, for 0 to 2 pi, I have two solutions, pi over 3, 5 pi over 3. All right, now let's start. As we're understanding this, we can probably go through some of these a little faster. Although actually, this next one is going to be a new twist. It looks simple enough. Tangent of theta equals -1. Of course, trying to solve for theta. Tangent theta is a little tricky because when I think about the unit circle, sines and cosines are easy, but when I do tangent, I've got to think sine over cosine. So I've got to go with the unit circle and find any angles where when I take the sine over the cosine, it equals -1. So first of all, I've got to find those angles where the sine and cosine are equal in terms of magnitude. And of course, that occurs at all those square root of 2 over 2, which are all the pi over 4, 3 pi over 4s, whatever. But then also, I have to realize that it needs to be -1. So even though these magnitudes are the same, one of these is going to have to be a negative, either the sine or the cosine. So let's first of all think which quadrants we're going to be in. In which quadrants is the tangent negative? Or another way of thinking it, in which quadrants are the sine and cosine not the same sign? And I believe that happens in quadrants 2 and 4. So now I'm going to go, first of all, let's go to quadrant 2. And let's see where the sine and the cosine have the same magnitude. And of course that occurs at 3 pi over 4. At 3 pi over 4, the sine is square root of 2 over 2. The cosine is negative square root of 2 over 2. So the tangent of 3 pi over 4 is going to be -1. And if I go to quadrant 4, I realize in quadrant 4, it's 7 pi over 4. So initially, I have two solutions. Of course, what happens with the tangent, like sine and cosine, is you can go around and around the unit circle. But here's what's interesting. You would think maybe I would have two solutions just like I had with sine and cosine, but tangent's different in that the tangent actually, sine and cosine starts repeating every 2 pi because it's one trip around the unit circle. Tangent's interesting in such that the tangent repeats every pi. I'm not going to take the time to explain that to you. I'm just telling you now, anytime you're solving an equation with a tangent, instead of adding 2 pi over n, you just add pi over n. And when we do that, we actually don't have to write both of these anymore, because you realize when n is 1, I'm going to get my 7 pi over 4. So the thing I want you to realize is that for tangent, when we write our general equation, we don't add 2 pi over n, we just add pi over n, and it makes it a little simpler. Now, if they want to know what the solutions are between 0 and 2 pi, now here's some good practice. I'm going to go ahead and write my n's over here. When n is 0, theta is 3 pi over 4. That's inside my range, so there's one solution. When n is 1, 3 pi over 4 plus pi, or I could say 3 pi over 4 plus 4 pi over 4. Seven pi over 4 is still less than 2 pi, so that's a solution. If I make n equal to 2, 3 pi over 4 plus 2 pi, well, you can sort of see if I'm adding a positive angle to 2 pi, obviously it's going to be larger than 2 pi, so I don't even have to actually do the math. I can just stop and say it's not going to be a solution within my limits. So here's the specific solution. All right, now let's do another one. So here's a new twist. See, hopefully you're understanding how to do those. And now here is something different. Sine of 2 theta equals 1. The big difference is, if you look at all the examples up until now, all my trig functions were just theta inside. Here, inside the trig function, I have this 2. So it's sine of 2 theta equals 1. Here's the way I'm going to teach how to solve this. We're going to use what's called substitution, which is something maybe you've done in other kinds of problems in algebra and math. What I'm going to do is I'm going to take whatever is inside the trig function and I'm going to call it or rename it u. And then I'm going to substitute it. So instead of writing sine of 2 theta equals 1, I'm going to write sine of u equals 1. And now this looks like sort of what we've been doing before, where of course we called it sine of theta equals 1. Now we're going to have this u here instead of theta, but it's the same idea. If I try and solve this, basically I have to ask myself, what are the angles where the sine is 1? So the sine is 1 at pi over 2, and that's the only place on the unit circle where the sine is 1. Of course, once again, I can go round and around the unit circle, so my general solution is going to be u equals pi over 2 plus 2 pi n. So now I've come up with this solution, but the key thing is, realize this is a solution for u. When I started this problem, I was trying to solve for theta. And because I did this substitution, I created this variable u, and I've solved for u. But that's not, if someone asked me to solve this equation, and I said, well, u equals this, they're going to say, what is u? We asked you to solve for theta. Like, what is this u you're talking about? So what you have to do is, even though we do this substitution to be able to, in a sense, solve this equation, we're not done, because the last step is I have to convert all my u solutions back to theta. It's almost like at the start we went from theta to u, and then we figured out our solutions, and at the end I have to go from u back to theta. And all you do is you go grab your original definition when you first defined u. U equals 2 theta. And now I'm going to go over here. This is my u solution, so I can say also u equals 2 theta from up here, but u also equals pi over 2 plus 2 pi n. And what I do now is I just take these two expressions here, this equation, and solve for theta, right? So if I do that, I have to divide both sides by 2, or that's the same thing as multiplying everything by 1/2. And I get theta equals pi over 4 plus pi n. So now I actually have solved the equation for theta. So let's review what we did. Because inside my trig function it was not just theta, I had to use substitution, so I said u equals 2 theta. Whatever is inside the trig function, I'm going to call that u. So then I have sine u is 1, and I solve for u. There's my solution for u. But then I have to convert u back to theta. So I said u was originally the same as 2 theta, but use also this right here. And there's my general solution. Now if I want to go between 0 and 2 pi. Once again, I'm going to go off to the side and I'm going to start counting up my n's. When n is 0, theta is pi over 4, and that's definitely within my range. So I say, well, that's a solution. Now how about when n is 1? When n is 1, we've got pi over 4 plus pi over 4 plus 4 pi over 4. It would be 5 pi over 4. Is 5 pi over 4 less than 2 pi? Yes, it is. So that's also a solution. So with problems like this, I keep bumping up my n until my angle is larger than 2 pi, and then I stop. So how about when n is 2? Well, once again, I plug in 2 for n. Pi over 4 plus 2 pi, obviously, it's going to be larger than 2 pi, so I stop. And then here are these two solutions. And let me do one more problem before I end up doing a third video, it looks like. This is similar to what we just did. Looks more complicated and uglier, but I think we can figure it out. Cosine 4 theta minus pi over 4 equals square root of 2 over 2. And we're trying to solve for theta. So once again, this is a problem where if you look inside the trig function, I mean my theta's there, but I got a bunch of other stuff too. So how I'm going to solve this, I'm going to take all the stuff inside the cosine, inside the trig function, and I'm going to define that as u. Once I do that, then I can do the substitution, and my original equation just becomes cosine of u equals square root of 2 over 2. I can solve this. If u is my angle, I say, okay, let's go find the angles where the cosine is square root of 2 over 2. And I realized this is going to be first and fourth quadrant. First one is going to be pi over 4. Second one is going to be 7 pi over 4. And of course, I have to add the 2 pi ends. So these are my solutions for u. However, I'm trying to solve for theta. So now I go back, and I go back to when I first defined my u. Easiest thing is just to take and write over here 4 theta minus pi over 4. And do the same thing here. Then I'm going to take both these equations and solve them for theta. So let's take this first one. This first one is pi over 4 plus 2 pi n equals 4 theta minus pi over 4. So if I solve for theta, I'm going to add pi over 4 to both sides. Pi over 4 plus pi over 4 ends up being pi over 2. Plus 2 pi n equals 4 theta. Now if I divide both sides by 4 or multiply everything on both sides by 1/4, it's the same effect. What do I get? I get theta equals pi over 8 plus pi over 2n. So that is that's my first solution. But I've got a second solution. So I have to do the same thing. I have to take 7 pi over 4 plus 2 pi n equals 4 theta minus pi over 4 and solve this equation for theta. So if I add pi over 4 to both sides, over here I get 8 pi over 4. Actually, I get 2 pi plus 2 pi n equals 4 theta. Now if I multiply both sides by 1/4, I get pi over 2 plus pi over 2n equals theta. So my two general solutions, just to make this nice and neat, are pi over 8 plus pi over 2 times n. And the second one is pi over 2 plus pi over 2 times n. Now, that's my general solution. If I'm looking for the solution where my angle is between 0 and 2 pi, so here's where I go over here. I start with n equals 0, figure out my thetas, and keep going until my thetas are larger than 2 pi. So when n equals 0, this first one, theta is pi over 8, and the second one, theta is pi over 2. Those are both less than 2 pi. So there's a couple solutions, but I need to keep going. What happens when n is 1? Well, this first one, pi over 8 plus pi over 2, pi over 2 is really 4 pi over 8. I think it's 5 pi over 8. And the second one, pi over 2 plus pi over 2, it's pi. Both those are still less than 2 pi. So those are both solutions. So we just keep increasing the n's until our angles are bigger than 2 pi. Now when n is 2, it's going to be pi over 8 plus pi over 2 times 2, which is pi. Pi over 8 times pi. It's like 9 pi over 8. And here, when n is 2, pi over 2 plus pi, isn't that 3 pi over 2? Wow. We're up to 6 solutions, because these are all less than 2 pi. We have to keep going till we exceed 2 pi. When n is 3, oh boy, 3 pi over 2 plus pi over 8. I'm going to have to do that over here. If I get this common denominator, it's 12 pi over 8. Looks like 13 pi over 8, which is still less than 2 pi. And then when I plug in 3 for here, 3 pi over 2 plus pi over 2 is actually 2 pi. Now if I look here, so definitely 13 pi over 8 gets included. But 2 pi, you notice here, they usually say it's actually less than 2 pi. So if it equals 2 pi, you actually don't include it. So my second equation, I'm finally over my 2 pi. The first one, I'm not sure. I have to keep going until I'm over 2 pi. However, when n is 4, when I plug in 4 up here, pi over 2 times 4 is 2 pi. So then I realize I'm over it also. So for this, what did we start with? Wow, way at the top. For this equation, there are actually 2, 4, 6, 7 different angles that are solutions to that equation. In other words, you take any one of those angles and you plug it in here and it's going to work. All right, so this is our second video on solving trig equations.